Good afternoon, gentle readers. Welcome this April 22nd of 2024 to this episode in the installments of the essays of Moment and Motion, the mechanics of motion. So what I hope to do today was to continue reading from this entry in the Dictionary of the History of Science, which is a tome compiled in the 1980s that purports to estimate the extent of the theories of the concepts of the language of science and its overall course of discoveries in terms of the theory of the day and the knowledge of the day and in the language of the day. And what 40 years later, 30 or 40 years later, still very, very well represents that notion of this segment of this time. And so what I hope to read from is this section on mechanics. And here in Moment and Motion, as we've been talking about mechanics in classical mechanics, it's all matters of the laws of nature that dictate the motion and the interaction of bodies, of massy bodies, of physical quantities that entail their extent and their mass and their velocity and their location with regards to any such matters of the interaction of massy bodies as mechanics. There gets involved the statics and dynamics with regards to the Galilean, which is generally the most simple linear motion, and at some point in time in the relativistic or highly dynamic with regards to space-time and the effects of space-time contraction with regards to the speed of light in the theory of general relativity or the general theory of relativity. That then what gets involved here more so is the issue about the kinetics and kinematics. This is where the kinetics is the consideration of the linear impulses and those things which are exactly juxtaposed, the equal and the opposite, in the sense of being quite totally linear and in one dimension. Whereas the kinematics raises the entire consideration of the rotational and the abstract form of a fulcrumless lever. That simple machine, known for the mechanical advantage of a place to stand and the moments of the arm of the lever, it also as well reflects what happens when any two bodies collide at a glance, and thus, according to the incidence of this glance, make for that there's always an unlinear component to any of these sorts of interactions. And so what gets regards then with the quantities of the momentum in the linear and the inertia, which is kind of underdefined and which here is being explored and established as a linear quantity and in terms of its units in the dimensional analysis. And then with regards to the rotational and the kinematic and the moments of inertia, and as with regards to what it entails when the again in theory with just the classical actions, also the theory with the relativistic actions of the highly dynamic in with regards to the rotational setting and the general theory of relativity has that when there's arrived at these concepts like space contraction, when an object gets moving fast enough that it starts bringing its space along with it, vis-a-vis that it always is and does, that there's differences of that. The dynamics differ in the linear and the rotational. So that's something that I hope to explore because, first of all, is that any theory of relativity results being classical in the limits. Here when the relative motions of objects are not large. But at the same time, there's very ideas of the rest exchange momentum and what are made of the true centrifugal as a fictitious force, yet that it really well explains what is the content of the system, besides that an instance, but what will come and go with it. That in this sense, the rest exchange momentum becomes one of these central concepts in what otherwise are the quantities of the system, and the conserved quantities of the system, those which maintain always a continuum law, result being somehow non-conservative in why we have what's called, in the same context as there are fictitious forces, what's called pseudomomentum, where the fictitious forces are what's in the theory today, and to be explained as how they're real forces, and what are the what is momentum is to be explained as how it is pseudomomentum. The entry that was started to read from last time was from this history of the Dictionary of the History of Science. And so back in the 1980s, this was a tome, a compilation of the contribution of many researchers and scholars in the field of science, in the history of science, in the language of science. And so even though then that's been that long ago, it still largely affects to reflect the theory of scientific discourse then and now. And so these days, most researchers, to gain a cursory and casual knowledge of the subject, will look directly to the internet and find Wikipedia, which these days is a great source for lots of the background and theory and history of these things. And I see as usually quite improving most of the time, over time, at least as well or as better as other sources available on the internet that aren't, for example, just a copy of the Dictionary of the History of Science. So the entry mechanics, I just looked it up, and what it is it's written by a fellow named Heilbrom from the University of California at Berkeley. And so I will read from this for a while and see what it intends to entail about the theory of mechanics. So it's after these other entries about mechanics, mechanical equivalent of heat. Well, see, we have this thermal second law and all these things with regards to entropy that are supposed to explain everything about this statistical mechanics and all that kind of stuff. Mechanical materialism, mechanical philosophy, see corpuscular philosophy, man-machine, materialism, mechanical reduction, mind-body dualism. Mechanical reduction. Mechanical reduction is the representation of phenomena not evidently mechanical in terms of the primary qualities of matter in general. The mathematization of physics was not achieved using either system. In the late 18th century, when physicists came to prize quantification, they introduced special imponderable fluids as agents of heat, light, electricity, and magnetism. During the first half of the 19th century, they devised mechanical representations of light and heat. At mid-century, the discovery of energy conservation suggested that all phenomena ultimately could be reduced to mechanics. So this is the statistical mechanics, and after Boltzmann and the Clausius and Rayleigh and Kelvin and the second law of thermodynamics, not to be confused with the first law. But with regards to then the conservation laws, Noether's theorem then has that's the great rule of the invariants, an invariant being something which does not break, that the invariant of each symmetry arises, that there's a conservation law, that in the mathematical models, then wherever there exists this sort of symmetry, there's an invariant, there's a conservation law. Well, that's further refined and defined these days, or here, that instead what that entails is a conservation law and a continuity law. So that it really evolves the phase transition over this sort boundary, and whether or not that's a matter of usual dynamics or not. And that helps to explain some things that would otherwise end up being called symmetry breaking, to make for what is then described in terms of symmetry flex, which in a sense is symmetry breaking, but only at the extremes, only where these running constants start to change. Because at the high or low energies and configurations of the experiment, or even at the angular and this unlinear, is where mathematically there's a big gap of how it changes from point to point in a usual and real and regular sense. With regards to the classical formulas, the flatland of the usual perspective and what happens in the outer product that then collapses back into that to make the inner product. So in that sense, the conservation laws are still very well stood up as laws of physics. There's also what goes on to make for these running constants. They're also laws of physics. Compassing this reduction became the explicit goal of physics. Almost all physicists advocated reduction. So reduction is great because everything ends up being energy. Instead of mass, the quantity, it's like, well, we got a formula for mass-energy equivalency. We got a formula for energy equivalency among different forms and manifestations of energy, like potential here, potential there, potential everywhere, energy. So that reduction is great. And then the idea of figuring out what's going on in the geometry, why these issues arrive to reflect each other and make these potential differences in energy, whether that's the potential energy of a lifted body or the potential energy of water at a waterfall, or the potential energy of a circuit and potential difference and making potential energy and voltage. And this theory around here, it's a sum of histories, what's arrived at and making for things why the path integral works in quantum mechanics after the stochastic interpretation and with the modern continuum mechanics attached to it. And also with the statistical mechanics. The sum of histories, and that being then where it's going is the sum of potentials. So there's a reduction to that, while at the same time in the theory among the physical quantities and all that being energy, and the second law of entropy still has that there's this dual complement of entropy, which is everything to fall and go to the floor by the second law. Because the oldest original law of physics is what goes up must come down. So today, that's the second law of thermodynamics, that everything kind of descends to what is this conserved energy in terms of heat, because heat is localized, and at the same time it moves, it radiates in a very general sense in the space frame. That's why second law of thermodynamics and the statistical mechanics is used today at the fundamental level to explain everything up to a point, and just to arrive at the usual laws and then where and why they don't work out. The other day I was looking at the golden ratio is phi, and so phi is familiar, like in a seashell it grows out at a ratio of phi, that a box and a box within it of the same ratio of side to side is phi, the golden ratio. So another thing about phi is that phi minus 1 equals 1 over phi. It's the only real number for which that's solved. The x minus 1 equals 1 over x. So and then that's also saying something like x squared plus x plus 1, or x squared minus x plus 1 equals 0. So then I just changed the sign on that, and I was like, well, when I solve for this, what do I get? And then I found this number, and it's like 8.75 something, and it's the molar gas constant. Well, what's the molar gas constant, you might ask? And I mentioned this a little bit last time. I was like, well, it's a mathematical constant in mathematics. It has no real place being a physical constant. It should be just a symbol and divided out somehow. But the Clausius Clapeyron law, which is part of this whole statistical mechanics, is got right there. It's like, well, this is a mathematical constant. You know, it's one of those things that helps then affect to figure out how that's related to the Boltzmann constant, which is a physical constant, and one of the very few physical constants as far as scientific digits go of these scientific numbers in the physical theory at all. And so it's interesting to try and figure that out, because it would achieve more of this goal of physics's reduction. It's reduction to a fundamental elementary theory. Almost all physicists advocated it. The British cultivated it most vigorously. Their practice included 3 different sorts of representations: ad hoc models of limited scope. Here that reflects on the other day from reading from the next entry, which we're going to read it, about the severe abstraction of classical mechanics. It's like, well, we've reduced it to the Galilean, and that's after the Mertonian school. It's like, well, whether we call it like the tendency forward and the tendency back as P over R or P minus R. Well, you could write it either way, and then everything else just has to be written in that. It's been figured out that force equals mass times acceleration is pretty much what lines up with that. At a given instant, in a given direction, at all, everywhere, vis-a-vis the outer product, and all the sum of all the histories and the sum of all the potentials, the many-body system insofar as it is. Incorporating distance forces as well as pushes, general fundamental models that eschewed distance forces, such as Kelvin's vortex atom of around 1900, and description in terms of Lagrange's equations or another general formulation of mechanics. So today you'll find Lagrangians everywhere, because, well, what's a Lagrangian? Well, it's a very particular sort of formation of a system of equations, but it just means whatever's parameterized by time, because everything's a function of time. So today, that would be pretty general. But it is interesting here to notice this got otherwise what's going on with the near field and far field, or that we have in these recent discussions here, differences between the length of something and the distance it travels. That then it's just the velocity times time is the distance traveled, and the units are like seconds per second, which cancel to be dimensionless. Yet at the same time, that's an extended dimensionless quantity in a sense, as was discussed here, and bringing in the notions of the mathematical dimensional and dimensionless resonator and alternator with regards to the stop derivative from descriptive differential dynamics, a walk integral, a run derivative, and a pause integral. That these kinds of different integro and integro differ systems help affect to reflect what is, doesn't have solutions yet, doesn't have forms yet, doesn't have formulas yet, but what is, according to definition, the way these things have tendencies and propensities. Like this, their tendency is the second law of thermodynamics, and the propensity is anything that makes an actual dynamic in that. That it's always at equilibrium, but always going to equilibrium at the same time. Some of histories, some of potentials, constantly, instantly is evaluated everywhere, constantly in motion. For this tendencies and propensities and attenuation and dissipation, for this oscillation in these models of waves and restitution as for what established this standing. And to that, even like an object at rest on the table is at rest as of all the sum of things it could be. So that's not too far afield to help explain that objects in motion stay in motion, objects in rest stay at rest, and then for this second law is what goes up is falls down by gravity, and then force equals mass times acceleration, but whichever one of those is first, you know, that there's equal and opposite of these things according to what we say is a classical value, the real value of inertia and momentum about the energy in it today, according to the kinetic energy in the inertial, and the potentials that make up all this entire far field. So, this article goes on to say, in their enthusiasm for ad hoc models, the empirical, the British differed from their colleagues. They recommended such models not as literally true of nature, but because they were easier to reason about than the equations to which they gave rise, and suggestive of effects and interconnections which one might not otherwise have guessed. Says see models. The program of mechanical reduction rapidly advanced statistical mechanics, ether, until circa 1900, physicists began to take electrical theory rather than mechanics as normative. I don't know if that's so, because Kelvin says everything's kinetic, so. But the Maxwellians and that which goes into the quantum mechanics that explains things of the optoelectronic, and with regards to that being electromagnetic, is a thing. There's here considered careful balance of things about mass and real and potential kinetic energy, and charge and real and potential electromagnetic energy, those being quantities, and the speed of light and the transmutation or the lifetime of the proton. So kind of like the neutron, the electron, the photon, and the proton. Those making up for what then are in our fundamental field theory, the four fundamental forces of strong nuclear force holding together the nucleus, weak nuclear force, and electroweak having to do with the radionuclear with regards to the emission of radiation, and so that light lives in that somehow, and the tachyonic, and then with regards to the electrical force. Where's gravity? It's a strong nuclear force. Everything just kind of falls in and ends up being the same force. You mean there's a way to approach the general theory of relativity on one side and quantum mechanics on the other, this field theory, and gravity just kind of sitting in the middle? Yeah. What's quantum gravity then? Well, it's just that there's the entire space frame makes for that. It just has this most minuscule, weakest, fleetest, fastest force everywhere, gravity. And then the objects don't actively gravitate. They're not always working all the time, pulling each other in, pulling me back in, as the old sketch goes. Yet instead, they're falling together. And then the reason that then ends up two bodies come to rest together, like us on the Earth, or anything in their orbits about each other in the geodesy and the world ions, according to general theory of relativity, classical mechanics, Newtonian mechanics, modified Newtonian mechanics, and the post-parameterized Newtonian description of the ephemeris Earth, is that objects just kind of block other objects by the shadow of their gravity. And thus in this manner, there is a pretty unified theory of all physics, where here the idea is then to explain what happens for mechanics, specifically in the classical, to help arrive at this kind of theory of some potentials, still is along the lines of that the classical, which is considered the real part in the theory today, the potential all being just kind of what balances out the conservation law, is a part of the potential itself, that the potential fields are the real fields, and it just works out the same that the classical is part of that in the classical limit. See? So these things is kind of as this entry on mechanical reduction effects to relate are not necessarily intuitive or of the sort of things that may be formulated so well and easily. But mathematics owes physics the formulations, how these things add up. And then we point to Fritz London and superfluidity and what happens when the fluid model has part of is the flux is fleeting. because abstractly it is, these gravity's weakest quantum particles just constantly flying ultramundane everywhere from every direction in every direction really are a thing in terms of what that's the particle model of quantum gravity that has then with reflect to the fundamental forces, and then with regards to general theory of relativity and frames and spaces and frames, in the mechanics, the object or body is mostly the space within its atoms and moves that along. And then to get into why and how there's this rest exchange momentum in theory, in classical. The program, the electromagnetic worldview, in which the prime mechanical quantity, inertial mass, is interpreted as the resistance to acceleration of a massless electrical charge, did not quite succeed. But in relativity theory, Newton's equations were subordinated to Maxwell's, and in quantum theory, the literal ascription of mechanical quantities to microscopic entities was explicitly rejected. And this entry was also written by Heilbrom, who's now written this entry of mechanics. Mechanical theory of light, see elasticity light. So light is just this fleeting. Light is the special theory of relativity's principle, is the L principle. Light speed is a constant. Mechanics. Two complementary approaches to the theory of the equilibrium, statics, and motion dynamics of gross bodies descended from antiquity. In one, exemplified by Archimedes' treatment of the lever and of floating bodies, quantitative results are achieved by severe abstraction from the behavior of real bodies. So this severe abstraction is everything from air resistance to friction to the reasons why the formulas, as they started to add up, then they would not, that they figured everything out by just rolling things down ramps. And then the simple machines started to get invented, and these provided mechanical advantage. And so as soon as they got figured out that the ramp, the inclined plane, the lever, the pulley system, which changed so much. And then with regards to things like the screw and I'll have to research some more. What are there? Because there's 7 simple machines, and those are only 4 or 5 of them. And then with regards to then how boats float and this kind of thing was the other kind of thing with figuring out how to design a seagoing craft. That these were the wonders of technology. The foundation of statics and hydrostatics thus were early established, and through association with Archimedes' partly legendary feats, became the model for the application of mathematics to practical physics problems. The second approach, exemplified by Aristotle's teachings about motion, works with the essences and accidents of bodies as they appear to be. Several principles fundamental to medieval and Renaissance natural philosophy resulted. So this is this Mertonian school, the latitude of forms, which is basically Cartesian in the coordinate setting and explaining rise over run and these kinds of things. The distinction between natural and violent motion. This is where there's an idea that we have from Galileo that what goes up and comes down and it happens parabolically because gravity's acceleration is constant down. But the idea of the violent motion is that when you throw a spear or a football or a bullet with rifling, then it starts with this spiral action and it's spinning. And so it goes straighter, and whether that's it's posited that, well, that must be an aerodynamic effect because there is no effect ascribed to it by that kind of motion. Because otherwise the idea is that the spear would go up in a straight line and then fall off and go down. So just kind of like the ballotone is the ballet dancer who's accumulated this energy in their body and exchanges it in lift-off or something like that. Then the idea of this violent motion is like, well, it starts kind of with this activity in it, because violent doesn't necessarily mean as of carnage, it just means active. And so then this idea is that these notions of the real centrifugal really do, expect to explain the javelin, the football, and the rifle bullet, or rifling, which have well-known effects and are very much studied in the empirical with regards to their practical application. Renaissance natural philosophy resulted. The distinction between natural and violent motion, the requirement of a conjoined mover. So this is a conservation of all the forces that the application of action has, that there's a prime mover of sorts, and then we got into our unstoppable and immovable objects and these kinds of things. And the lever, the general idea of the lever everywhere, the lever. And the doctrine that finite directed motion implies the impossibility of the existence of a space void of resisting matter. Space. Medieval natural philosophers built on Aristotle's doctrine in two principal ways. One centered on the impetus theory of the late 13th and 14th centuries, which brought the conjoined mover into the body. And so this is still just that inertia and bodies of motion stay in motion, which brought the conjoined mover into the body. The initial mover conveys a particular quality that expires as it produces its effect. And this is just drag and other forces that are affected by any interface of the thing, that otherwise the minimal energy occurs with regards to these things. In John Buridan's circa 1220 AD influential version, impetus would endure if unopposed. He conjectured that it might be the cause of the revolutions of the heavens. So in these talks here, there has been talk some time ago about theories of cosmology, the Ptolemaic, the Copernican, the ideas where it comes from, whether that comes from inside the Earth, from the sun, from the North Star, or where otherwise the moments, kind of like that old picture of the galaxy on a T-shirt with a little arrow to the one of the spiral arms saying, we are here, kind of thing, to the concentric circles, the immobile celestial spheres, or these theories of cosmology, how does it go, up to Kepler and the after the epicycles, which kind of explain the position visually of these things according to a model of circles about circles, that they're the elliptic model, and it was just determined that the same area is transited in the same time, and according to inverse square and the universal law of gravitation, these kinds of things. The second scholastic innovation, going far beyond Aristotle, was a mathematical description of categories of motion, uniform, constantly accelerated, etc., and of possible relations between impressed force and velocity produced. The description treated by the method of latitude of forms yielded, among other results, the Mertonian rule, after Merton College, Oxford, famous in the 14th century for its calculators. In motion uniformly accelerated from rest to a velocity v, the total distance traversed is the same as that covered in the same time by motion at constant velocity v over 2. So we know this today as Galilean, the Galilean invariants, and the constant acceleration. And here has been trying to get figured out the infinitely many higher orders of acceleration. There's no such thing as constant acceleration. There's no such thing as a constant force. Force is a function of time with regards to smooth acceleration and deceleration and meeting and parting and starting and stopping. Only 600 or so years later, the description: in motion, uniformly accelerated, the total distance. Among the relations considered, the laws of Thomas Buridan, circa 1290, 1349. The velocity is on the order of log p over r, and Avrampace died in 1138 that the velocity is on the order of p minus r, where p and r are impressed force and resistance, deserve notice. Although they may look like applied mathematics, these laws belong to the scholastic tradition, and particularly to nominalism, being treated as examples and possibilities, not as testable and correctable descriptions. Well, you see, they kind of make for a mathematics that would have to reflect that everything else expressed in those arithmetic operations would just have to be expressed as about the implicits and the orders of things. And today, as we have everything being linear in terms of the orders of the units, and the linear and the rotational, with regards to that nominalism is a model of that thing. And so if the entire world made it so that was the only meter stick, it would still be the same everywhere else. It would just be in those units, or according to the derivations, it's about those units. Like if the only meter stick was like an inchworm per 5 minute hourglass, then it would be about and around in those. So for the author here to say, it's like those are formulaic approaches, but they don't result. What we have is kind of like the simplest reduced form. Still has it there. They declare that this relation is like this mathematical relation. This mathematical model models that physical model. That's all there is to it. Whether that's sensible, fungible, and tractable, and consistent, then says, well, it's got attached to everything else in the physical model according to mathematics. Mathematics has only got one mathematics. It has a variety of different models, like of large numbers and stuff, because the numbers are super standard. And similarly, these classical and physical models, see, there's these super classical models. They're all extraordinary. We don't have to care about that, because in the classical mechanics, what we want to arrive at is only very, very, very least amount of that just still keeps it sensible, fungible, and tractable. Although they may look like applied mathematics. Mathematical statics was pursued during the Middle Ages primarily by the school of Jordanus de Namore, 1220, who introduced the concept of positional gravity, or weight as modified by the constraints of the system. So weight is mass in gravity. There was discussion that there's basically the difference between the acceleration due to gravity of a massy body and the g-forces in gravity, which are like on the order of the units. They're kind of like, it's like, well, any direction you're going according to acceleration is the g-forces equivalent to gravity. And then this positional gravity includes things like these local moments of inertia, the balaton, these issues with the violent motion, and these kinds of things. The rotationally symmetric, which establishes an inertial sink of a sort. Jordanus resolved the weight of a body supported on an inclined plane into components parallel and perpendicular to the plane. And this is just like Galileo is like, well, I got a cannonball and just drop it off, or a cannonball and shoot it out. They both drop at the same rate. So helping separate the components, same as the latitude as forms, same as rise over run, separating the components. And he obtained the law of the balance or lever by calculating virtual displacements from equilibrium of the weights considered positionally. His approach, transmitted in the Renaissance by Peter Apian and Niccolò Tartaglia, influenced Galileo and Simon Stevin. Stevin was a Nederlander. Stevin distinguished clearly between statics and kinematics, the study of the motions of bodies without regard to the agents of motion. Here, as I employ that term, I intend very carefully and didactically that it's still good. And so freed statics from unnecessary complications introduced by analysis of virtual displacements. Fictitious. Displacement occurs only in approach to equilibrium, and its application to statics holds only as a non-physical limiting case. Stevin formulated a statics independent of such kinematical concepts and provided a basis for the generalization of the principle of virtual displacements. Well, I looked to study that some more. The virtual is kind of like the potential, is kind of like the fictitious, or otherwise here with the usual notions being the pseudo, the quasi, or the degenerate of these notions of the pseudo-differential, degenerate intervals and points, the quasi-invariant in measure theory, with regards to this virtual displacement, or virtual particles in the field theories. What's a virtual particle? It's like, well, it's kind of whatever is the echo left over when, according to the conservation law, it shouldn't be on the other side. It's the ether, it's the virtual particles, it's the neutrinos, it's whatever's virtual. Vis-a-vis the partners, the partnerinos, and the antiparticles and the virtual particles. And the potential is just like, well, what's the real part? It's like, well, what we can measure with this stick here and this clock here, and that's potential. Limit the potential and the fictitious. What's the true centrifugal? Well, we just call it negative and say it's on the outside instead of the inside. Does this theory still need negative time? No, it does not. It's recalling the previous discussion, which got into quite a long-winded aside as to why in the mathematics of the Eulerian and Gaussian there's all this stuff in the complex numbers, is no, there is not necessarily that attachment to this mathematical model's analytical model and some numerical methods in the implied with regards to the mathematical model geometry, these motions. Stevin formulated a statics independent of such kinematical concepts and provided a basis for the generalization of the principle of virtual displacements. And Stevin is also famous for these like infinite numbers. He's like, they didn't have any infinite numbers. He's like, well, what if we have infinite numbers? What do the ends look like? So, and he's also familiar for other things that go into that are still part and parcel of the modern theory today. Galileo took an Archimedean approach to the schoolmen's problems and conjectures. In De Motu, circa 1590, he attempted to amend Aristotle's treatment of motion by using Avampochi's rule and Buridan's competus of impetus. He thus rejected the impossibility of vacuum, the existence of levity, and the strict differentiation of natural from violent motion. Both involve acquisition of impetus. By 1604, he had broken more fundamentally with tradition by making his goal a quantitative description of an apparent oxymoron, ideal real motion, which he supposed would occur if air resistance and other usually small disturbances did not exist. In general, Galileo analyzed motions, not their causes. He consequently sought, and sometimes misidentified, cases amenable without reference to causes. An example is his claim that bodies show no effect in virtue of their participation in the Earth's motion, principle essential to his defeat of physical arguments against heliocentrism, the Copernican revolution, but inconvenient and even contradictory to his chief argument in its favor, the tides. We have Coriolis and the tides. Another associated principle is circular inertia, which Galileo sometimes substituted for Aristotle's natural motion in the Dialogo, 1632. So that gets into a couple different concepts. One is that for things like Coriolis and the tides, and the Casimir effect, and something about the Compton effect, in electromechanics, and with regards to Casimir and the optics between plates, and the Coriolis force is about the Earth, and the winding, and these kinds of things. They're fictitious forces. Well, they're very real. They're kind of fictitious in the theory to help explain what, why, question words. And then here, this idea that this circularized inertia is going on vis-a-vis the moments of inertia. And for rotational motion is kind of like, well, that's the idea that there's this part is reflective of either side, and where it goes with, what are the causes of motion, and what are the results of the motion, and where does that go? We just figure, well, it goes with the object. Well, whatever pushed it is going the other way. That's this third law of physics, the equal and opposite interactions. So the three laws of physics are, for object in motion stays in motion, object at rest stays at rest, and two objects that change motion move in equal and opposite directions. The conservation law. Although he doubtless did not perform the demonstration from the Tower of Pisa, this is that the ball of lead and the ball of wood were dropped at the same time and fell at the same rate and landed at the same time. Galileo certainly confirmed his principal results, which were identical with one form of the Mertonian rule, by experiments on inclined planes. These results in free fall velocity v and distance s are respectively gt and gt squared over 2, combined geometrically with a consequence of Galileo's impetus theory. Without resistance, a violent motion will persist with constant velocity, yielded parabolic trajectories for projectiles. Galileo gave many theorems about ballistic motion in the Discorsi, but the degree of abstraction made the results impractical. Now, just like the falling bodies bit, is that the rolling bodies bit has that, according to the moments of inertia, they will vary, at least in that very smallest amount, because the force is inverse proportional, and as it gets closer, it gets that much closer. The balls have a center; they're not point masses, and so they start rolling slower, the heavier ones, and they start falling slower, the heavier ones. But then they gain. So it's to be pointed out that these things have a beginning and an end. Force is a function of time, including gravity. Galileo's revolutionary concern with ideal real motions became the theme of progressive 17th century mechanics. Descartes, among others, insisted on the principles of relativity of motion and of rectilinear inertia. And many corpuscular followers sought the laws of collision to describe the encounters of billiard balls. Descartes provided too many such laws and placed them at the head of his Principia Philosophiae, 1644. They were amended by others, notably Christopher Wren, John Wallis, and Christian Huygens, who also gave the first published expression for the centripetal acceleration required to maintain constant circular motion in their Horologium Ausculatorium, 1673. The postulate of composition of velocities, used implicitly by Galileo in his derivation of ballistic trajectories, was made explicit in 1687 by Pierre Varignon and Bernard Lamy. The principle of conservation of a vector or directed momentum emerged clearly from this work. So Varignon and Lamy, Lamy, have momentum as a concept and a quantity coming out of this. Most of these principles, rectilinear inertia, composition of velocity, conservation of momentum, were formulated or reformulated in or around the three axioms of motion with which Newton began his Principia in 1687, or Principia, a synthetic work capping the tradition begun by Galileo. Although Newton concerned himself with the nature of body and force, he tried, not always successfully, to give his results in the Principia in terms of the velocities, accelerations, and other ideal real observables, which is a great approach, The Principia established the basis for the theory of motion of mass points under centripetal accelerations in absolute space, relativity, and set the problem of treating a system of bodies interacting via accelerative forces diminishing in strength as some power of the distance. Showed in the case of gravitating spheres and spheroids how to obtain observed macroscopic effects from assumed microscopic causes. And as an aid to destroying Descartes' theory of vortices, subtle matter, it gave an approximation to a quantitative theory of motion in resisting media. A byproduct was a novel theory of the propagation of sound, which gave its velocity as a function of the pressure and density of the medium of conveyance. Waves. The 18th century systematized and extended Newton's approach and synthesized it with the mathematical methods of Leibniz and Johann Bernoulli I, who generalized the principle of virtual velocities into the anchor of statics. Leonhard Euler subjected the dynamics of mass points to analysis in his Mechanica, building on the work of Daniel Bernoulli, Alexis Claude Clairaut, and Jean Laurent d'Alembert. See here in the descriptive differential dynamics, we have after Clairaut and d'Alembert that they have very much some of the first forms of the simplest linear things in the integral equations, and that's why the identity dimension, which is kind of the envelope and a singularity of all of those, it's kind of as relevant as like zero is in terms of conservation laws, that these are kinds of the things. He also devised the fundamental equations for the flow of inviscid fluids. These are the Newtonian and non-Newtonian fluids, are compressible and incompressible. And through such concepts as moment of inertia and instantaneous axis of rotation, he made the theory of the motion of rigid bodies, Theoria Motus Corporum Solidorum, 1760. Euler. Another systematization occurred through synthesizing principles apparently opposed. See, this is the idea of this juxtaposition, or the apparently opposed, the complementary duals that add up all together. After a long dispute between partisans of Leibniz and of Newton, agreement was reached about 1740 on the proper measure of the force of moving bodies. Momentum and vis-viva were recognized as different integrals of the second axiom of motion, and the propriety of Leibniz's principle of the conservation of vis-viva acknowledged for elastic collisions. Well, that's great. So now for the pseudomomentum, vis-viva is this concept since antiquity of this. And so just saying that, as Heilbrom says here, different integrals of the second axiom of motion is that gets into why. Now that is helping to explain that is a thing. Now that'll have been gathering some dust and left behind in the development. And so then trying to figure out what its real attachment is, or if it's just kind of, a partial off to the side, is something else to get figured out. But it does help to reflect that it's kind of the staying power of this kind of thing. The grand synthesis of 18th century and analytical mechanics is Joseph Louis Lagrange's Mécanique analytique, 1788, starting from the principle of virtual velocities, already refashioned to apply to dynamics by imagining a moving system to be at rest under suitable impressed forces, D'Alembert's principle. Lagrange set forth general mechanics and hydrodynamics as a matter of pure analysis. He worked not directly with force, but with its integral over space. Potential, which breaks the immediate connection between motion and its causes expressed in Newton's second axiom, he boasted that he needed no diagrams, no appeal to geometrical intuition to set up and solve mechanical problems. Lagrange needed only the Lagrangian, the difference between the kinetic and potential energies, and the calculus already developed into a supple analytical tool by the perfecters of dynamics. One of Lagrange's notable results was to incorporate a generalization of Maupertuis' principle of least action, extremum principles, into a system, and this is the sum of potentials is the least, that make effect. In 1744, Maupertuis had replaced Fermat's principle with a similar law that required light to travel more quickly in optically denser media. 1747, he applied this proposition that all material processes occur in such a way that the total action created is a minimum to collisions. The action of a system of particles is the integral of sigma I of the pi, qi, p and q standing for momentum and position, respectively. Euler showed that in the case of motion under a central force, the integral of the quantity p dq is an extremum, not necessarily a minimum. Lagrange made delta f p dq, delta integral p dq equals 0 general equilibrium and freed it from the error of final causation with which Maupertuis had encumbered it. So this is nominalism in effect. These are mathematical methods being applied, and they affect to relay their application in that model with this inchworm-hourglass. Better ones. A true minimal, as exposed to extremal, principle was formulated by Carl Friedrich Gauss in 1829, principle of least constraint. With the acceptance of the wave theory of light, it was recognized that Fermat's principle applied to geometrical optics and Maupertuis to particle dynamics. And so then we get into the Hamiltonians and the great success of that, Navier Cauchy, Saint Venant, James Clerk Maxwell, and a bit more on this entry to be continued at a later date. So that's what I want to read today, and what I've learned about is vis-viva came back in the picture, vis, viva, viva, vis-viva, vis-viva or vis-viva, and so that helps me understand that in terms of the pseudomomentum and the virtual velocities, that's going to be a part of it. And then there's that Maupertuis is pretty cool. You got Euler coming into play with regards to why he basically provided this extra stuff relevant to making the applied the Newtons, which is a great synthesis of everything from Galileo to the Newtonian school and Kepler and all this stuff with regards to the system of the world, Kepler's system of the world, and Newton's system of the world. And then there's with regards to de motu from Galileo, and that again being part of this nominalism, and it's like this is measurable, these are real observables, this works great, and especially with regards to, and these formulas are simple. That's the goal is that adds up exactly to that, and then with regards to this the theory of the mechanics, then there's a lot condensed into such an article as that, so it's quite appreciated. And I wondered if I can find something from early Greek philosophy, and this is Barnes' translations of these sources. Philotas of Croton says that our bodies are compounded from heat. There's your thermodynamics right there. 5th century Pythagoreanism. What is moving moves neither in the place in which it is nor in the place in which it is not. Zeno does away with motion, says Diogenes. Having said that if the whole force moved the whole weight of a certain distance in a certain time, it does not thereby follow that half the force will in the same time move the whole weight half or any fraction of the distance, nor will every fraction of the force which moved the whole weight be capable of moving the whole weight for a given time and over a given distance. Aristotle thus resolves the argument which Zeno of Elea put to Protagoras the sophist. Tell me, Protagoras, he said, does 1 millet seed or the 10,000th part of a seed make a sound when it falls? Protagoras said that it did not. But he said, does a bushel of millet seed make a sound when it falls or not? When he replied that a bushel does make a sound, Zeno said, well then, isn't there a ratio between the bushel of millet seed and a single seed, or the 10,000th part of a single seed? Protagoras agreed. Well then, said Zeno, will the same ratios not hold between the sounds, for as are the sounders, so are the sounds, and that being the case, if the bushel of millet seed makes a sound, a single seed, and the 10,000th part of a seed will also make a sound. That was Zeno's argument. So he got the infinitely divisible. It says that's from Simplicius, Comments on the Physics, from Zeno. Zeno's argument. Aristotle discusses Zeno's argument. Now, Aristotle has got prior and posterior analytics, and Aristotle has got a lot of what's in it. So it's important to read into the context what he means and in what context he's saying it when things like this do and don't apply, because he's got both. And Zeno is similar. People say, well, what did Zeno do? It's like he proved that there can be no motion. It's like, no, he proved that it's the way it is, and you have to think it out that it is. Virtually nothing is known about his life. Well, anyways, that'll follow some more later. Hey, I shall so hope, as I say at the close of these episodes, that all is well with you and yours, and things are great and fine and well, and that as springtime has come upon us, and it's still late in the day, and with the sun shining bright and turning the executive desk globe, that you have a great day. Carpe diem, tempus fugit, all that. So on.